Hello and welcome to Calculus 1. Yes, every one of my videos starts like that. So we're going to start with overview of chapter 1, which is pre-calculus. We are going to review about functions, the most important concept within calculus. We perform calculus on functions. You take limit of f of x, you take derivative of f of x, you take integral of f of x. So for the most part, you are concerned whether the relation you put down is function. And we have to define function first, which is going to be the question on your first exam. Verbatim, you have to state it. Sometimes I have questions which say state the definition, state the theorem. Just to give you some free points, because free points are always cool, right? So we start with definition of a function. Function is a rule which assigns to each x in the domain a unique y in the range. The important words are rule, domain, range, and the word unique. The word unique is the one that makes this definition of a function. If you take that word out, this becomes definition for mathematical relation. So mathematical relation is something that it's a weaker concept than a function. Any formula you write is mathematical relation between variables you put. Like equation for a circle is a mathematical relation. It's not a function because uniqueness is ruined there. We'll see that. So word rule is equation or a formula. That's what the word rule means. Domain is input. Range is output. And the word unique, as I said, is the carrier of the entire definition. Notation is f of x. And we usually say y equals f of x, where y is the output, x is the input, and the graphical representation for this would be x comes in, function changes it into a y. So if y equals f of x, we say x plus 7, then f of 3 is 3 plus 7, which is 10. You can understand this as x equals 3, y equals 7, 3 comma 7, the point that you are going to plot on the graph. So the relationship between these things, observe that by plugging in 3 into this formula, the only thing that you can get is 10. There's no way to get anything else. You plug in 3, you get 10. You plug in -2, you get 5. That's the uniqueness part. Unique answer. Unique answer. When each member from domain, which is the input, maps into a single output, which is the range, we have the function. when a member of the input maps into two different outputs, not a function. So situation on the left is okay. Situation on the right is no. You can think about this. This is clear, right? But then look at this. Just look around. You're all different inputs in this classroom, right? And you're all in the same classroom. And this is the guy that was drilling over there. So that's a function, that's okay. What's not a function is you being at RVCC and at home at the same time. See that? That's not a function. Does that make sense? Light switch, right there. What's its function? What is its function? Light switch. I don't know. Well, yeah, I want to know what. Exactly. Okay. You worried that I'm going to cause an earthquake or something? You don't, right? So that light switch has a function to control uniquely these sets of lights. I can rewire that switch to do something else, in which case that switch will uniquely do something else, whatever I wire it to do. That's what we do in MTWR. So when you're thinking about the function, you have to have this notion of uniqueness. Single input or multiple inputs produce single output, unique output. You are allowed to have multiple inputs produce single output. That is okay. The best example would be x squared. Y equals x squared is a polynomial function. And if you think about this, you have, let's go with 2. Negative 2 and positive 2 both produce positive 4. And that is okay. That's a function. So f of negative 2 is 4 and f of 2 is 4. It is okay to have that situation. What it's not okay to have is the sideways parabola, because that one on a single x, let's say 4, will produce positive 2 and negative 2. So this is not a function. It's not a function. So it's okay to have multiple inputs produce single output, because as you can see, the negative 2 cannot produce any different number than 4. Where over here, you have y of 4 producing positive or negative 2, which is not good. So not a function. Circle is not a function. Its equation is x squared plus y squared is equal to r squared. And when you draw, so I spent the whole summer practicing drawing circle. I am perfection now. There we go. What's funny? Look, it's perfect. Say radius is 2. This is x squared plus y squared equals to 4 equation. for the circle. And when you look at this circle, if you draw a vertical line, we call this vertical line test. You see that line cuts the graph twice. It cuts it here and it cuts it here, so it produces two different y values, not a function. So we use vertical line test to visually determine if something is a function or not. For vertical line test, if the line cuts only once, as you can see here, it's a function. Over here, cuts twice, not a function. So if it cuts more than once, immediately not a function. We use vertical line test because it's easy. Great. Why is this important? I already said so. We perform calculus on functions. You take the limit of the function, chapter 2. You take derivatives of function, chapter 3 and 4. You take integrals of functions, chapters 5 in Calc 1, and then 6 and 7 in Calc 2. And then rinse and repeat in Calc 3. So functions are important to understand, and you need to have a function in order to perform. You cannot integrate circle. You can differentiate circle, but it's only one section where we're going to do something interesting. Other than that one section, for 2 chapters, you guys will be working with functions. We understand that functions compute values. As I said, x comes in, function changes it, y comes out. Y equals x squared minus 3. Y of 5 is 25 minus 3 is 22. Number comes in, number comes out. Now, the function is technically representing all possible combinations of input and output using that particular formula at the same time. So it's really taking infinitely many of these pairs and writing them compressed into a single statement. So we can have equation like y equals x squared minus 3. When you have multiple functions, because at the end they are numbers, they can be added, subtracted, multiplied, divided, squared, square rooted. You can do anything, and then you can plug one function into another function, and you can go on like that. Because remember that the input was 5. I can obtain that number 5 using a different function. So what can I do if I have 2 functions? Oops. What can I do if I have 2 functions? I can add them, subtract them, multiply them, divide them, make sure g is different than 0. I can square root a function or put nth root there. You can put function to a power, f to the n. You can find the inverse of the function. And function composition. That one is going to play a key role in some of the things. I mean, all of these, but function composition tends to be the most challenging for students, and to be one of the most important ones of all of these. Now I want to demonstrate something really cool. Say that f of x is not learned in pre-calc. I don't know why. Say that f of x is a simple x plus 3. And g of x is x squared minus 1. let's talk about two worlds that we can have. Let's compute f of 2 and g of 2. So I have 2 plus 3, which is 5, and 2 squared minus 1, which is 4. How much is f plus g of 2? What happened? 4 minus 1, yes. What happened? It's 3, of course. Look, it says 3. Pay attention. Very good. I was just testing you. And everyone except 2 of you failed. All right. So f f plus g of 2. How much is that? F plus g. What do you think? Why 8? Why 8? Yes. Very good. Nice. So, if you are to add these two functions, you can add them here or there, anywhere. So if I create f plus g, it will be x squared plus x plus 2. When you add and simplify all of this, right? So x squared plus x, and then 3 minus 1 is 2. And now if you plug 2 in there, what happens? 2 squared is 4, plus 2 is 6, plus 2 is 8. You see that the functions, people say, oh, they behave like numbers. Because they are numbers. That's why. They have to behave that way. Now, what you see in here with addition holds for everything. If you are to go and do long division of these things and get terrible decimals, the division of 5 and 3 will give you the same answer. It will always give you the same answer. It has to. Because that's how the whole system works. And there are no exceptions, which is why this is infinitely cool. The next part is graphing. Oh, no. Sorry. Hold on. The next part is the function composition. Extremely important. Title. F composed with G is f of g of x. And I will verbalize that and say plug g of x into f of x. That's what it means. What were our functions? F was what? What was f of x? X plus 3? And the g of x was x squared minus 1, right? So what is our f composed with g? F is the boss, so g gets plugged in. So it's g plus 3. G is x squared minus 1 plus 3. The whole thing is x squared plus 2. This is the function composition. Do you want to see the function composition at work? What you call in real life, because this is all imaginary and fake life. You want to see it? Does this have a function? Does this have a function? There you go. So f composed with g. All right? This was g, right? It has a function, it has all of these. Oh, by the way, does anyone want to go into teaching mathematics, STEM, like physics and stuff? Is anyone interested in that? I'm asking because of this folder. Yeah? All right. Okay. So that's that part. Now I can put this on the side and put the behavior correctional device in front. What? There we go. Yeah, it reaches. The only people I can't reach is the last row, but I will walk up. Now, how about G composed with F? Which function is the boss now? So it's going to be f squared minus 1, right? Which means x plus 3 squared minus 1. How do we square x plus 3? Nice. Don't forget the middle term. So now we have both examples together. So number. So you have function f of x, function g of x. Now guys, those can be square roots, can be absolute values, can be technically anything. And then you have the composition. The first one is the outer function. The second one is the one that gets plugged in. So you see that instead of this x, we replace g, and then we plug what g is, plus 3, which came from f, and we have together. Here, g is the main. So if you look at this from far away, this is x squared minus 1. But we are replacing every x in that problem with f. Well, we only had one x, so just that's f. And now you have this. So I will have 2 exercises for you to try. First one is f of x equals x squared plus 3x minus square root of x, and g of x is equal to x. Yeah, x squared. It's fine. Maybe I can... Yeah, let's make it spicier. Here. There we go. So let's compute f of g. Now this is the part where you should, you know, meet the fine people sitting next to you, check your answer. Work stuff out. I'm trying not to drink. What happened? Oh, I don't need.
No, it's Dean selling off his money.
All right. What we are looking for is f of g of x. We are going to plug this equation into every x of the main outer equation. So we have g squared plus 3g minus g minus 1. Every time I write g is g of x, the whole thing. So g squared, which is x squared plus 1 squared, plus 3 times x squared plus 1 minus square root of x squared plus 1 minus 1. We have x to the 4th plus 2x squared plus 1 plus 3x squared plus 3. These annihilate each other. That's the math term right there. So you have a square root of x squared, which is x. Beautiful. So minus x. Collect like terms. X squared, x to the 4th plus 5x squared minus x plus 4. He's like, pay up. No. Great. Here's the next example. You've seen this one in pre-calc. G of x is equal to f of x plus h minus f of x over h, and f of x is equal to, let's say, x squared minus 3. Does anyone remember this? Yes? All right, great. Does anyone remember the name of that? Yeah, what's the name? Nope. Oh, not yet. Difference quotient. When you are learning the names, please stare at the thing. Look at the screen. Everyone, look at the screen. Ready? Difference quotient. You see that? Naming convention. Difference quotient. It's the same thing when you see this. Difference of squares. Right? So pay attention to those kind of things. The names are very closely related to what it actually is. So difference quotient. So what's g of x equal to then? Which part is the function composition? Is everything function composition or just a part of it function composition? Very good. Only this part is a function composition. The rest you get to copy and paste. Good. Let's see how it goes. Okay, so again, this is another problem from Pre-Calculus 1, which you learned in Chapter 1 when you did function composition. This is not like previous problem. In previous problem, you placed all of G within each X in F and worked out the algebra. Now, you have, this is like putting a Lego set together. You have a piece that you have to assemble. You have a piece that you just need to plug in. And then you have a piece over here that you just need to copy, right? This is, it's like 3 different things that you need to do within the same problem. So one more time, piece that you need to assemble, piece that you need to plug in, and a piece that you need to copy. So it's different than the previous example. Now, you follow the formula and you follow notation, so this is why you have to learn the notation and know what's going on. When we say the definition of a function is what it is and its notation is f of x, that means that this is all of the function, which is that piece. Now, observe that in this case here, it's modified. So when I say f of x, and then I plug in 3, or then I plug in a flower, whatever I plug in here is what replaces every x in that particular equation. So, by that being said, if I have f of x plus age, every x of this equation will be replaced by x plus age. So, to create the piece f of x plus age, I have x plus age squared minus 3, which is x squared plus 2x age plus age squared minus 3. Don't forget the middle term, the 2x age part. Now, the problem is not done, because all I did is I created this piece here. I still have to plug everything in. Replace this now. So, I mean, we can color code if you want to. We replace this piece with that. F of x is what it is. And then divide by age to get to the final answer. So now g of x, which is the new function that we are obtaining, is going to be the division line over here, x squared plus 2x age plus age squared minus 3 minus x squared minus 3 in these parentheses, and then everything divided by age. All we need to do is to perform algebra here. We should be good. X squared plus 2x age plus age squared minus 3 minus x squared plus 3. X squared and x squared minus 3 plus 3, they're all gone. Observe that the remaining terms in the numerator all have age. Kick it out. And now age dies. For the answer, 2x plus age. This is a procedure that you really need to know for this class. Section 3.1 on derivatives is going to use this in every example, because this is your derivative. You will just have another thing in front which will say limit age goes to 0 for each one of these. So we'll cross that bridge when we get there. But the whole procedure that you see in this particular problem, start this, I don't know, do something with this, make sure you can find it. When you do the homework for chapter 1, make sure you find these problems and do 3, 4, 5, 15, whatever you need to, right, to operate on the level that is necessary. This procedure is procedure to determine the derivative of the function. Good. Combining functions and so on. Inverse. The undo, all right? Just as in life, you don't get to undo everything. In mathematics, you don't get to undo every function, every calculation. For instance, consider two functions, f of x, x plus 3, g of x as x minus 3. It should be clear that one undoes the other. If you add 3 to a number, by subtracting 3, you will go back to the old number. So, if f of x, say f of 5, you get 5 plus 3 is equal to 8. Then you feed 8 into g, you get 8 minus 3 is 5, which is where you started. We say that the g of x is actually inverse of f, because it will undo whatever f does. Another simple example for this would be, say, f of x is 2x, and then g of x is x over 2. So f of 3 is 2 times 3, which is 6. And then if you feed 6 here, 6 over 2 is 3. So again, that's what happens. But then we get situations when this doesn't work this well. For instance, say f of x is equal to x squared, and then everyone screams, well, of course, g of x equals square root of x. Well, no, no, no. Because f of 3 is going to be 9, right? And square root of, so g of 9 is the square root of 9 is equal to 3. You say, well, that's exactly what happened. Well, not until I try this one. You see that? You don't get to retrieve negative 3. You can only retrieve positive 3, right? So clearly, this one is not working as well as the previous one. So now we need some definitions, theorems, and things to fix this and know when the function can undo 100% and when it undoes partially. OCD in mathematics is welcomed and important, all right? So we'll talk about that. Yes?
If you square root 9, you get plus and minus 3, right?
No. That's when you square root both sides of equation, you get that. When you square root number 9, you only get 3.
Okay.
You can never get negative 3 from square rooting.
Okay.
Because the square root graph, which we are going to cover later, that's an amazing question, actually. It's a very, very common thing. As you can see, square root of x only gives us positive y values. We can never get a negative 3. So we are going to cover that. That's amazing. All right. So what is this thing with the inverse? First thing that we need to understand is that every function has an inverse. But not every inverse is a function. You have to see, it's a layer, extra layer. So anything can be inverted. But the inverse you get is not necessarily a function. So we're going to see how this works now. To fix the issue that I have in a previous example, I'm going to say that f of x is x squared and g of x is equal to plus minus square root of x. Now observe that my notation is clearly different and I have that plus minus in front of the x. Now this is going to undo 100%. Right? You are going to get positive 3, you are going to get negative 3. You see that? But what's the issue now? This is no longer a function. Because the positive branch graphs here, the negative branch graphs here, which fails vertical line test. So, we lose a function, we gain 100% inverse. So there are some things that you will have to pay attention as you go through calculus. This is going to be important in one of the sections later on, I believe in chapter 4 somewhere. But nevertheless, it shows up, so worth mentioning it. There are other ways of fixing this as well. Another way to fix this problem would be to restrict the domain. You learned this in pre-calculus 2 with trig functions. None of the trig functions have an inverse function until you restrict the domain. When you restrict the domain, you start getting functions back. So how do you quickly check if the function has an inverse function? It's called horizontal line test on the original function. You see, horizontal line, if it cuts twice or more, the inverse is not going to be a function. So horizontal line test tests if the function has inverse function. One more time, every function has an inverse. And then the next layer is not every inverse is a function. Some are functions, some are not. And that's determined by the horizontal line test on the original function, f of x. To compute the inverse, we swap domain and range, and then we just unleash the algebra. So inverse swaps domain and range. In mathematics, for our calculations, we swap x and y. So say you have 3x to the 5 plus 1, right? That's your f of x. What's the inverse? We write as y equals 3x to the 5 plus 1, x equals 3y to the 5 plus 1. Move 1 over, divide by 3, and then finally solve y equals 5th root of x minus 1 over 3. You will write that the inverse function is 5th root of x minus 1 over 3. So try f of 2. 2 to the 5th power is obviously 30, right? No, that's fourth power. 32. So 96, 97. So we get 97. When you plug that into inverse, 97, you get the fifth root of 97 minus 1 over 3, which is the fifth root of 96 over 3, which is the fifth root of 32, which is 2. Keep tracing and plugging things in. The core here to understand is that the inverse is going to undo calculations which the function performed. Very important rule is that if you compose function with the inverse, you get x back. We can test this with easy functions, hard function, doesn't matter. It will always work. It's a theorem. So earlier I had that f of x is x plus 3, and inverse was x minus 3. Oh, actually, I should write the other one as well. If you compose inverse with the function, right, if you swap them, you still get the same x. So no matter which way you compose them, you always get x back. No or, and. So both of these hold. So if I compose f, do you have to do it on the first day? I think that this tablet has the excitement meter in there. So anytime I get excited, it immediately like resets me to. That's me being angry. Function composed with the inverse. So it's x minus 3. No, I would never throw the tablet. What? Actually, does anyone have an Apple thing that don't need? I'll throw that one. Come on, please, please. And that takes care of it. I guess it's time for a break. Come on. Why? The interesting thing is that this only happens on this tablet. The previous tablet is not giving me these issues. So this is actually the newer version. And I don't know why it's doing this. I tried everything. All right, actually, you know what? Let me do it myself. OneNote is cleaning up from the last time. All right, fine. Ah, cleaned up. All right, perfect. What I think is happening, it actually gets dropped from the cloud, from OneDrive, and then it starts in the background trying to reconnect or whatever, and then it starts going crazy. Good. So we're done with the inverse. The shortest story about the inverse is just the undo. If you compose function in inverse, you get x, and that's it. The next part, set the tone, and sense the tone actually. Graphing. You do not have graphing calculators. This calls for a restart, I think. So, Calculus 1 and 2, almost all graphs are 2D, so on XY plane. We have the x-axis, the y-axis, numbers 1, 2, 3, 4, and so on, -1, -2, -3, and so on. Positive y-axis, negative y-axis. All of these, right, are, so this is a standard, and all of these numbers exist in between, right, to positive infinity, negatives to negative infinity, and so on. Really? Now, what you see here is called a coordinate system. It's not a graph. When you draw a function on it, it's a graph. The line of a function is a graph. So this is a coordinate system, and once I put a linear line on it, let's say, then this line is called a graph. So that's something as a notation, I would say. Whatever. What do you need to know? You need to know constant function. And a constant function like y equals 3 is just a line through 3. You need to know linear function. Y equal mx plus b. This is your b. You have slope m and all of that stuff. Quadratic. Y equal ax squared plus bx plus c. Radical. Now, square root of x is the basic thing. You can have a square root of f of x, in which case it's much more complicated. But we are going to have sections in calculus that will address graphing crazy stuff. Rational functions. I'll say p of x divided by q of x, both of these polynomials. The cheapest is 1 over x. That's the cheapest, but the whole spiel, if you remember your 2.6 for pre-calc 1, that's that. Just a little line over here. 6 trig functions. We are mainly concerned with sine x and cosine x and tangent x. However, others do show up, and they're very easy. Just invert these cups. So you would put, for cosecant, you would put this cup instead of looking down, looking up. That's not a big deal. What else? Oh, exponential. Holy nightmare, I forgot. I forgot the exponential function. Y equals a times b to the x. And then we have them as increasing or decreasing, so growth or decay. We'll deal with that later. And logarithmic. Log base a of x, which look like this. And I'm leaving the whole section here for absolute value. How does the absolute value of x look like?
I think it was like a sharp V.
Very good. Sharp v. How about x squared? Very good. It's itself. Now how about sine x? How about ln x? How about e to the x? What's the absolute value of e to the x? Very good. E to the x. Every function that originally is above x-axis is going to be itself. If it dips below x-axis, it's going to be different. So let's say y equal x is a 45-degree line through origin. And then y equal absolute x is going to be whatever is under x-axis will be reflected up. So you get the V shape. Because this portion over here of the line that was negative is reflected up. If you observe x squared graph, as you guys suggested, everything is above the x-axis, so y absolute x squared, everything is still above x-axis. So the graph doesn't look anything different. So for absolute value, we don't get to learn case by case. We get to learn that you are not allowed to have anything below x-axis. So I will ask you to draw the graphs. I'll give you a few moments. Y equal sine x, which we know just the principal period, right, looks like this. So what is the absolute sine x? And then ln x. What would those look like? It's right there. Right. So for sine, or just have two bumps up there. For this one, we have that. So whatever was underneath bounces up, and that's it. I wish you talked more and interacted more. Eventually I'm going to go around and pick a random person and ask what are the names of people sitting next. But not today. All right, good. So now, what we do with these graphs? Say on the exam, you have a question that involves a limit, and the fastest way to answer that question is to look at the graph, but you don't have the graph in calculator, and the function looks like this. Y equals 3 over x plus 2. So how do we graph this? Well, in stages. When I teach pre-calculus 1, I usually ask students to have a separate graph for each of the stages leading up to the final graph. But then now that you are in calculus, if you can do everything in one step, perfect. The 3 multiplies every answer by 3, right? Because this is technically 3 times 1 over x plus 2. So this 3 is going to vertically stretch everything because it makes every y value 3 times further away from x-axis. Observe, if your original point was supposed to be at 1, this 3 will put that point at 3. If the point was supposed to be at 2, times 3, it's going to be at 6. So you can see, and if it's negative, it will go down and it will go down. So you see that there is the vertical stretch if you multiply by 3. If you multiply by fractions between 0 and 1, it will squish them, right? So the 3 doesn't change the shape of the graph, it just stretches it. The shape of the graph is impacted by the function itself, what I call parenting function or default function, in this case 1 over x. So we know that 1 over x graphs like this. This is 1 over x. And then we know what plus 2 does. When you add 2 directly to x, it shifts to the right, no, it's left. So it shifts to the left, which means that the vertical asymptote that used to be at 0 moves to -2. And the shape remains the same. And now, so this is 1 over x plus 2. So that's the stage 2. You have the default function, and then the plus 2 shifted, in this case, to the left. And then we have times 3. Now, times 3 is really not going to change things much. It's just going to make it turn quicker, like that. So this is it. 3 over x plus 2. So we do this in stages, and if you can do everything in one shot, awesome. If you never learned any graphing, and if you are not planning on learning any graphing, then employ the middle school method. Compute values for 1, 2, 3, 4, 5, 6, and connect the dots, like in a coloring book, right? There's always an option. But learning the graphing is important because at some point next Saturday, probably in the first half of the class, I will say limit as x approaches -2 from the left. That means you are observing this part of the graph, and you are observing how this shoots to -infinity. That concept is there for next class. So next Saturday. So graphs like this are going to be very important. Let's try y equals square root of 3 minus x, let's say. This one is a bit tricky. Okay, what's the parenting function here? Root x. Good. All right. So when you're looking at this, I'm going to quickly switch these. And then we're going to realize that there is a number that it's added or subtracted on x. So to get this correct, we have to factor that minus. So it's shift to the right, and it's reflected. And yeah, such is life. So we start with the square root function, and then we reflect. Now, the reflection is x, which means it's reflected on y-axis, and then we shift 3 units to the right. So we have this. So this is root x, this is root negative x, and then we move everything 3 units to the right. 1, 2, 3. Nah, terrible graph. Better. All right, so what was the original? Square root of 3 minus x. So, is this graph good? Well, let's check. What's f of 3? F of 3 is 3 minus 3 is 0. Square root of 0 is 0. And we do have dotted 0. Awesome, right? So if I'm computing this to check it, f of 3 is square root of 3 minus 3, which is 0. I have a point. 3 was the input. Y, 0 was output. And I have point 30, which is this point here. Great. Let's compute 7. If you try to compute 7, 3 minus 7 is -4. Square root of -4 is not real. But look, at 7, 4, 5, 6, 7, at 7, there is no function above it or below it, right? So that's good, right? That's good. Let's compute at 2. 3 minus 2 is 1. Square root of 1 is 1, and that's this point here. 1, 1. Awesome. So it works. This graph actually works. Now observe what kind of witchcraft I had to perform. I swapped the terms, put x first, and I realized that x is negative, and then I had to factor that negative. Now in pre-calculus, this is understood as a very tricky, difficult problem. You know, stay away from it. But we need it, right? Because this stuff is going to show up in the exponent of exponential function, or, right, you're going to have e to the negative x plus 2. The graph for that is going to go the same way. If we have to analyze the graph, if we have to take a look at the limit, if we have to figure out things, we need to be able to draw that. Again, no calculator. So it's practice, practice, practice. So please remember, any time when you have situations like this, right, adding a subtraction within a function, it's a little bit tricky. You have the example here. Would you like to, let's do one more. Exponential, logarithmic, something. What do you don't like? Logarithmic. Good log. All right. Y equals log base 3 of 4 minus x. Whatever. So try a little bit. So we start with a basic function, log base 3 of x. Goes through 1. We perform the same witchcraft. Log, we have negative x plus 4, and then we factor out the negative, we get x minus 4, which means that the function is shifted where? To the right side. So we again have a vertical asymptote. Vertical asymptote will go 4 units. We also have minus on x, which reflects it on a y-axis. My suggestion is to do reflection first, and then shift left, right, up, down. Always reflect first. So I reflect the log, which is now negative 1. So this is log base 4 of negative x. And then I shift everything to the right 4 units. So vertical asymptote is at 4. The log will go through 3. And it's going to look like that. Now, by the way, how are your logs? Is it good, bad, non-existent? Because it's going to be, we're going to have logarithmic differentiation, for instance, which is not just the derivative of logarithmic function. It's actually a procedure that converts every problem you see into a logarithmic function, and then using the chain rule differentiate. So it's going to be, and actually it is the most powerful differentiation technique. It's the one that you can learn and forget technically 2 chapters of stuff. So we'll get there. I'll give a detailed talk on the log then in that case when we hit that before, rather than giving it now and then again in 2 months. So I'll review log in detail. Prior to that point, we are not going to need details of logs in terms of compression, expansion formulas, or anything like that. Not even change of base. Well, primarily, the only thing that you really need to know now would be that, well, first of all, log is the inverse of the exponent, right? So there is a conversion formula, a to the b equals c. Log of base a of c is b, so you can convert back and forth. And then the base a can be any number in case that that number is e, then you would have notation ln. And if that number is 10, then you don't write anything. You just go like that. Those are the 2 most used bases, E and 10, in science and bio and finance and so on. So most of our application, 99.8%, all right, is assigned to these 2 bases, where E is obviously bigger. So those are the 2. And then you want to know that when the base matches the number, you get 1. Log any base of 1 is 0. There we go. This is the crash course without going into details of what the logs are, do, and all of that stuff. You already know the function. What's up with this pen? It skips. Log a of x, graphs like that, goes through 1. So that's a little crash course on logs. These are the things that you might see by the time we get to that big deal. And that's it. That's the pre-calc review. Your first homework due next class is chapter 1 review homework. Now when you open that thing like review exercises, you look at it and you see there are 52 exercises, right? And you say, is he insane? Is assigned 52? I assigned 52. Now, as I said before, some of you get the concepts like this or know all of this already. You do 5 exercises, you're good. Some of you do all 52. The goal and purpose of chapter 1 is to put everyone on the same level, which is we need everything from chapter 1. If you can't solve some of the problems from that homework, that means that you are not ready for Calc 1, and because of that, you will have issues solving problems. Whatever you've seen in this lecture so far were problems that are preliminary work for calculus, something you do in margins because you have to do quickly, manipulate something, right? Concepts that you need to know. None of these problems were calculus, but they will all be used and embedded in calculus. So you need to know them, especially the difference quotient. That's your derivative calculation, the long way, the definition. So the homework is going to be chapter 1 review homework for next Saturday, and then we'll see if we get to do how much else we get to accomplish. So this is the first part. I will restart the stream for chapter 2. We hit the break and then we'll see what else. Ciao.